Hi, welcome to your first quantum computing course, your first quantum computing lesson. I'm excited to guide you through this fascinating journey where we'll explore quantum mechanics, quantum computing, Qiskit through this practical code. You are going to be able to find it on the description for a GitHub repository. And let's start setting up our environment. Here you have for all of the scripts, all of the notebooks, you're going to have the list of install required packages. You can set them initially in your environment, so you don't need to install them there, or you can install it in the beginning. Depends on how you want to work with this. The installation requirements, here we're going to have some of the mainly libraries we're going to use. Remember, we're going to use Qiskit version 2.1.1, which is the most updated quantum computing framework for Qiskit, and Qiskit Air, which is the simulator that will run our quantum circuits on classical hardware. All of this we're going to be able to run it locally, and then here we can import all of these libraries. We have NumPy. This is mainly the classical mathematical operation and arrays. Matplotlib and Seaborn, which is going to be useful for creating the beautiful plots, and quantum circuits, which is the main class for building quantum circuits. R simulator, which is going to be the simulator for run it in our classical computer. Generate preset pass manager, which is the optimizer for circuits in execution, and a state vector, which is going to represent is going to be the function that represents quantum states mathematically. Okay. Okay. So, what is quantum computing? This we want to understand, like the quantum versus classical perspective. So before diving into the code, let's understand what makes quantum computing special. Classical bits are either 0 or 1, but quantum bits can be in a superposition, simultaneously both 0 and 1 until it measures. Here I present a real physics comparison that you can look into it, which works as a quantum coin flip, which is a Stern-Gerlach experiment. In general, is you send one quantum state through a inhomogeneous a magnetic field, and this one is going to interact with the magnetic field. In particular, they use for this experiment, they use silver atoms, which they were shot through an inhomogeneous magnetic field, as I mentioned. In a classical physics predicted a continuous distribution of deflections, so you're going to get like a definitive distribution of it. But here, instead of this, the atoms were deflected to only two discrete positions, which were spin up or spin down. So for a magnetic field in one direction, you can get both results, one or up, respective to the magnetic field direction. And in a classical perspective, you can have different states because the spin can point to different directions with different magnitude. Here we have two specific states, and this comes from the nature of the electrons in quantum mechanics. So this showed that angular momentum is quantized here in these systems, and in our case it's interesting because it's binary. So we can take this system as a quantum coin. When it goes down, it's going to be named tails, and when it goes to spin up, it's going to be heads. And you can change the nomenclature to 0 or 1. We use this in general in quantum mechanics, these symbols around the numbers to name the states. You can put actually anything on it, and this is named as ket, which is a general way for mathematics to represent a vector, a way of how a vector is. You can check more on this notation if you want to, but this is the thing that you need to know at least. And you can just represent the sum of these vectors, which is going to be a superposition, in the same way that you can sum coordinates You can sum vectors in general as coordinates and description of a state, and you can explain a state as a sum of 0 or 1. And one particular interesting thing is that in general, quantum mechanics do not restrict you to any particular set of numbers, of real numbers, so you can use complex numbers in general. Okay, let's go to the Qiskit part here. Okay, our first quantum circuit, the fair quantum coin. And here we're going to create a design of a simple, the simplest case of a quantum circuit where 0 and 1 are going to have the same probability. As you can see here, I explained that you can use the Hadamard gate. Remember that you have a vector. In general, states in quantum mechanics are vector, and by vector I mean the ones that you know. And vector, it's to transform, to modify, to change the direction of a vector, you need a matrix. So when you apply a matrix to a vector, you can change it, and then you can rotate it somehow. And for our case, we want to rotate the zero state to a superposition, to state where it's a mix of 0 and 1. Hadamard gates goes from 0 to this state in particular that you see here, where if you check the chances of this, the square of 1 over the square root of 2 is 0.5. The square of that is 0.5, so that means that you have 50 percent of probability for each outcome when it's measured. So in Qiskit, you can, here with the quantum circuit, you can get you create a circuit with one qubit and one classical bit. The first number is quantum registers and the second is classical registers. Then you can define the Hadamard gate, which is this qc.h, which is going to apply the Hadamard gate to the qubit 0. And this is the magic. The Hadamard gate transforms the 0 into the state that I put on top, which is equal, superposed on both states. And then we put quantum barrier, which is for visual clarity, is a visual separator in our circuit diagram. It doesn't affect the computation, but makes the circuit easier to read. So we can, it's clear to see it as us trying to understand the code. The quantum, the QC measure, it measures the qubit 0 and stores the result in a classical bit 0. This collapses the superposition into either 0 or 1, or at least is what it simulates somehow. In our system, do you think of the atom in the superposition of the electron of the spin in this atom, this ion? It's when interacts with the magnetic field that is measures, because measure and interaction, it's the same, it's equivalent in quantum mechanics. All the time that you say that you're going to measure something, because you're going to interact with the system. You cannot interact with it without measuring something. And there's a way in which Hadamard gates is not interacting itself, it's transforming it. So it's like guiding it, but it's not observing it, right? It's not checking the state. You don't know. When Hadamard goes to the qubit, it doesn't matter the qubit itself. You say that you're going to apply Hadamard to 0 because you have the previous knowledge that is 0 in advance, right? And the text here shows, the output shows our circuits schematically. You can see that you have the qubit that goes through a Hadamard and then goes to a measurement, and this notation means that the qubit 0 gets a Hadamard gate, then a barrier that's for easy visualization, and then the measurement, which is stored in this C, which is the classical channel where you store the information of this. Okay. And here there's another version of how you can plot the same circuit that you already create. You can get it here like in plain text if you want to, but you can also get like a more beautiful plot. This is one of the good things that have Qiskit, that is easy to observe, is quite of easy to visualize. Understanding the quantum states mathematically. Here, this text is mainly to write a lot of the information, so you can go directly to here, and it's a quantum state analysis. This is an explanation of what is above. Sorry, and in the initial state, if you imagine that you have description of a zero like this one, and the zero is going to be the state vector in this case, and if you want to represent it as a vector of two dimensions, dimensions 2, mathematically what you're going to have in Python is 1 plus 0, j, with j is the imaginary part. Remember that this in general is going to be a complex number in the first dimension, and in the second dimension is also another complex number, but because you only have information on 0, this is going to be 0 plus 0, right? And if you're going to get the state 1, this is going to be opposite, where 1 is going to be here. You can also have 1 with complex imaginary part, and it's not going to affect the probability itself, because the probability is defined by the norm, not by the face of the complex number. So if you have 1 imaginary part and 1 real 0 part, it's in from the probabilistic perspective is the same. It's going to affect this when you have superpositions, where the face is going to add to other faces, and then you're going to have interference of the faces. Then after the Hadamard gates, you're going to get some superposition, and it's going to be everything unreal still. If you check how the Hadamard gate interacts, it's going to let 1 over the square root of 2, which is this one, this 0.7, and this other 0.7, and then if you take the modulus of each of these components, you're going to see that this is going to be 0.5, which is here where I want to show you measuring the probabilities of this. If you define P as the probability of getting this zero state, it's going to be the norm of it. And the mathematical detail of this, it looks like this. The initial state, you're always going to define it like a state named C sub 0, which in our case is 0. And the Hadamard gate is the next state. You're going to have C1, which is the next state, and then you have this general one, right? This general one, which is then you can take the norm of each of these numbers and check the number that you get. What we show on top is that you can call this one alpha, and then this one beta, so you can define them as the constants of the system and of the state. And the normalization check that you need to do is that the square, the norm square of alpha plus the norm square of beta is equal to 1, because you need 100% of probability in total. You cannot have less or more than 1 here, right? You can check easily these calculations, that this is well normalized, right? Always that you have transformations on quantum computing, you're going to get also a normalized state. So norm is always 1, and it's one of the conditions here. Okay, so let's visualize the quantum state. You can get like a geometrical representation, the geometric representation of quantum states. So here we define a method named visualize Bloch spheres. So the idea is to print the quantum state itself. I mentioned to you that you have like a numerical complex, a complex value description. So for example, if you get the visualization here, check that the first initial state of zero is going to be something like this. If you have like x, y direction and z direction, you can define the entire system of the 0 plus 1 description as 0 being this on top pointing above arrow, and then 1 being the one that is pointing out below, right? And when you apply Hadamard gate, you're not going to get either 1 or 0. You're going to get a intermediate state that's here in this direction, which is half 1 and half 0, right? And when you measure this, imagine that you have the state, the mathematical description in this x direction, and you measure it with a magnetic field in C, which is the orthogonal direction to this. You have equal probability to measure it on 0 or 1, right? So this can be more complex to explain here. Then you could check how this base measurement works, but the idea is that you're going to measure it like in the initial basis 0 and 1, which is, if you notice here, the 0 and 1 basis here is on the z direction. So if you measure it like that, you're going to have a chance of getting 50% 0 and 50% 1. And here I name it like North Pole, South Pole, and Equator superposition state, like to make it easy to understand. But here's one of the tools, the Bloch sphere is one of the tools to visualize a quantum state for a qubit. Okay, so running our quantum coin, the single flip, we need to execute the quantum circuit. So flipping the coin once, we can observe what happens, right? So we're going to define this single quantum flip. Breaking down this execution, the air simulator is going to create our quantum simulator object that will execute the circuit on classical hardware. And then the generate preset pass manager is going to create an optimization pipeline that transpiles our abstract circuit into something that the backend can execute efficiently. So here is the part that usually you can check between these two in the case that you want to run it in an actual quantum computer on a server that you can maybe have access. In this part is when you're going to run everything somewhere else. And then, well, yeah, with the pm.run, this is how you transpile our circuit and you convert it into high-level gates into the specific operations our simulator understands. So all of this is going to happen in the backend. And then you can run the circuit as here I name it job, and this simulator.run. You define the transpile QC, and we put here one shot, right? Because remember that you have the chances to get any kind of result, and at the end you need multiple shots to understand the system and to actually get information out of it. But here we're going just to check what happens when we measure one shot. Well, which is the times that you're going to run the experiment. And then you have these results to get the counts, right? Which extracts the measurement results as a dictionary like 0 or 1, right? And if you go here, after running it, you see that the single quantum coin flip result in 1 interpretation, which is going to be heads, right? Is the state 1. If you check this and you run it constantly, you're going to get 0, 1, 0, 1, ideally in a 50%, at least on this case that we program, right? Okay, so now the power of statistics. Many flips is how you're going to get the information, the true information of these systems, and the quantum mechanic behavior emerges when we perform many measurements. So we are going to set like 1,000 times Here we put like shots as 1000, right? Defined as a 1000 for this method. It's practically the same as the previous one. So if you can check, the main difference here is how we're going to count them. We're going to count the numbers of tails here, extracting the zeros and extracting the counts of ones, and then checking out how it behaves. And if you see here, right, the quantum coin flip results in 1000 flips. For this measurement, we got 492 times, which is around a 49.2%, and 508 times, which is a 50.8%. If you increase the number of flips, this number ideally is going to reach 50%. Remember that here we are running it locally, so this is still a simulation. So this is not true randomness. It's not the true random nature that we want to. You're going to experiment that true randomness from a real quantum computer. Here we're just emulating, so we can get an idea on how these systems are implemented. Okay, so let's go for a data visualization dashboard. Here we have some of the results, and we want to create a stunning visualizations of our quantum coin flip results. And for that, we can have our this one create beautiful plots method. The idea is that you define here a lot of variables, colors, or stuff. This is actually not Qiskit at all. This is mainly just the plots. But what you're going to have here is that you're going to extract the data. You're going to convert the quantum result into a plottable format. You can going to get an histogram, a bar plot, a pie chart, a comparison plot, and add annotations on how to show the counts and the percentages. So actually, is the results. All the information that you have is from above, but here you want to just show the convergence of the results, and just like a easy way to understand them. So let's go here. This is mainly plots. If you can see that the quantum coin flips results, the Qiskit histogram that we put here, with what we said before, is around a 50%. Here I can show it in percentage. I have different diagrams here. It's more like the description of the outcomes that you wanted to, between the theoretical idea. The theoretical idea is that it's going to be 50%, which is the blue one here in the theoretical versus experimental, and the experimental is not ideally that. But if you check the convergence to theoretical probability, which is this plot of running average versus the number of flips, you can see that in the beginning, as even if you flip a coin that you have on your hand, you're going to get this behavior that is going to reach 50% when it's going to converge to 50% when you increase the number of shots, right? And then, well, you can estimate a deviation from the expected result, which here the absolute value at this point is 8. If you increase the number of shots, you're going to get closer results and a less absolute error, and you can minimize this one, right? So this is mainly it. Here I'm going also to explain some of the physics behind this. Remember that we always check on this concept of wave-particle duality. The idea is that if you think on wave or light or any linear system, you're going to have sums or mixes of the solutions of a linear equation. That is more general than the wave-particle duality. Usually you explain wave-particle duality to say like the electron sometimes behaves like a wave, sometimes like a particle, but in general what you have is a more general description, right? So here I'm just going to leave some details. Please don't take the wave particle duality too serious. It's just like a way to teach this kind of concept, which is not too rigorous. The idea is that you have a more general description with the superposition principle of quantum mechanics, but it's useful still. So our qubit behaves like a wave in this superposition. When measured, it behaves like a particle with a finite state, and it's exactly what it happens with photons and electrons. And then the superposition, as I mentioned, you can define it as a sum of the states 0 or 1. Usually you're going to use alpha and beta to define the complex probability amplitudes. And remember that these ones always needs to be normalized here, right? And well, the concept of measurement here is going to be always this interaction with the state, right? And the qubits exist in all possible states all the time. You just define the state, and then when you collapse the function randomly, it's going to give you a classical state on all the description. You can check this real-world analogy with the Stern-Gerlach experiment, but also you can have the same system with a photon polarization through filters or atomic energy levels in a spectroscopy, in case that you want to check any other system, physical system. And why does measurement cause collapse? This is like to go for physics. Is usually named one of the deepest mysteries in physics, but actually the interpretation goes more for a philosophical part of science, more like a descriptive part of science. If you can just describe what is happening, you can describe exactly that when you interact with the system, it collapses to a certain probability. So taking interpretations more like all of them could be valid, and all of them just are more aware of you to approach the concept, is not giving you more tools to understand it, right? What you need to understand is more from the mathematical description. And then let's go here. You have the interactive exploration, and we're going to get then quickly a bias coin, a quantum coin flip. Remember that you define the quantum circuit. You can create again your qubit. This the difference is that we're not going to apply Hadamard gate. Here we're going to get one qubit, one classical qubit, and the matrix that we're going to use is the rotation on y direction. And because it's a rotation, you can define an angle, and the way it's going to rotate in the Bloch sphere is not going to be necessarily 50-50. The same, you can create the barrier and the measurement. And then here in this block of code, what you're going to get is like testing different angles from 0 to pi radians, and you can run it also 1000 times here. This is like the same representation of the code before, and this 4 is just going to check different angles so we can see how it behaves. So go here, and depending on the angle that you decide to rotate it, you can observe that, for example, at 0 radians for theta, you get that from the 1000 shots, the 100% of them are tails. So it means that you rotate the state, or you didn't rotate it at all, and you leave it on 1 all the time, right? And another rotations, you're going to get different probabilities. Imagine that you start rotating in a bit, so you start getting a chance of getting 1, and this diminishing the probability of getting 0 by a bit, and then increasing the angle, you are going to get closer to 50%, and then you can again lose that ratio between them and increase the numbers of 1 until 1 is the 100%. Sorry, I made a mistake here. The first one was 0, 0. From 0 to 1, you can see how you can change the probability of getting 0 to 1 until you get from 100% of 0 to 100% of 1. And this is just by rotating the quantum state with a matrix. In the case of Hadamard, what we saw is that it's equivalent to a rotation of this case for 50%, right? So key takeaways of here and physical insights. I'm going to leave here some quantum concepts master. You know that qubits can exist in superpositions of multiple states. There's a lot of ways to define quantum gates, which are matrices. One of the ones here presented was Hadamard, and you can manipulate the probability amplitudes. The measurement is going to collapse when you interact with the system, and the superposition is then going to collapse to a definite classical state. And this quantum randomness is which becomes fundamentally different from the classical randomness. Here I leave you some of the experiments, some practical applications, next steps, and here you have some extra exercises for further exploration. I don't want to go too deep on this because if you want to check, then here is going to be on the script on the GitHub. And then thank you for the first part and welcome to the quantum world. We're going to try to go to another physical system and other concepts from Qiskit for representing these processes in quantum computing for the next session. Thank you so much.